Hi guys, this is Jeff Lendermon with GoEngineer. Welcome to my webinar on SOLIDWORKS Plastics. I'm going to go over some of the things for best practices to achieve reliable results with the SOLIDWORKS Plastics Simulation tool. So I'll go ahead and get started with a brief overview of SOLIDWORKS Plastics. There's 3 levels of plastics: Plastics Standard, Plastics Professional, and Plastics Premium. With SOLIDWORKS Plastics Standard, it was created for your part designers. It'll answer the questions of, will my part fill, where are my weld lines and air traps. We can look at sink marks and work with multiple gates. And if you go up the next step to Plastic Professional, you get everything within Standard, but it's designed more for your mold builders or tool designers. So you work with multiple cavity molds, family tooling. It's got a very powerful runner balancing tool, so you can make sure you've got a balanced shot and pressures between unlike parts of different sizes. It will do inserts and overmolding. So you can overmold over metal inserts or plastic inserts. It will simulate the 2-shot molding process as well. It will also do valve gating, so you can have multiple valve gates on a hot runner system, and it will actually do automatic valve gate timing, which is really nice as well. So you get a plot that comes out showing the timing at which the valve gates open. And then also with Plastics Premium, there's the advanced cooling analysis and the warpage analysis. So part of my webinar today, I'll be going over the advanced cooling analysis and why it's important with a study. So in my webinar today, the best practices to achieve reliable results, what I'll go over is some tips and tricks for a good mesh. We'll go through the meshing process within the software as well, and I can show some differences between the 2 different types of meshes that I like to use. And then we'll go over what to look for if your study indicates a short shot. Typically, you may get a short shot, your part will not fill. Sometimes there's some settings within the system that it'll throw a short shot and your part's not really going to be a short shot. So I'll go over those situations and what may cause that as well. And then the last is going over the cooling study and why it's important. So first I'll go over the different mesh types available in SOLIDWORKS Plastics. We have a shell mesh and solid mesh. The shell mesh is typically used on thin-walled parts, and we use it to obtain quick results in the early stage of an analysis process. Really, it's for something, a very simple part, just a simple shell or a flat plate or something like that, and just a basic analysis. I'll show you the shell mesh on this particular model that I've used in the software, and we can see the difference between the shell and the solid mesh and what may happen. And then a solid mesh can provide more accurate results for any model, thick or thin. So our solid mesh will provide a greater accuracy result for models with more complex and intricate geometry. So when I do a solid mesh, I'll use a hybrid, but there's also the tetrahedral mesh as well. So tetrahedral is putting pyramids of elements within the mesh on your model. And if we look at the 2 images that I have here, the top one is a tetrahedral mesh. And a best practice in the simulation is to have 5 mesh elements across the thickness of the part. Well, if we look at the top image, we can see there's only 2 or 3 going across in some of those sections. So we would actually have to go back and refine our mesh and come back and look at it again. Well, with the SOLIDWORKS Plastic, it has a hybrid mesh as well, as we see in the bottom image. The hybrid mesh will actually make it a whole lot easier to achieve this 5 elements across, because it automatically puts 2 layers of flat elements on the outer surface of your shell of the model, and then puts tetrahedral in the inside of it. With having those 2 layers on the outsides, we automatically have at least 4 for our mesh. So when we do a mesh, we get a mesh summary, as we see in that top box the solid mesh manual, the summary. Is it waterproof? It looks to make sure you've got a waterproof mesh. There's no holes in the mesh. If there are, there's editing you can do to fill them in. Number of mesh groups will tell you how many bodies you have. So if you have runner systems meshed as a separate body, or maybe you have water lines meshed or something like that, your number of mesh groups will increase. On this model, I only have a single model, so it will only be one mesh group. What I want to concentrate on are the bad elements, very bad elements, and the maximum aspect ratio. So in the simulation, what Plastics looks for, it has a recommendation of aspect ratio, which is the ratio of the triangle length versus width in your mesh elements. So a good mesh element will have a ratio that's less than 8, and a bad one will be elements with a ratio between 8 and 20. So typically, if you have a bad element less than 15%, you're okay. You don't really need to fix those. And then very bad elements will have a ratio above 20. These we want to always fix so we can get the most accurate results from our simulations. If we look underneath the bad elements where it says maximum aspect ratio of 34.2, in this case, if we look at the purple colored mesh element, even though it says 0%, there was like one mesh element in this model that I pulled up, and we have the ability to actually go in and fix this. There's different ways that we can fix our mesh through mesh editing. So the easiest ways is to do more mesh refinement instead of going in and editing the mesh, because you can drag the nodes around and delete and combine the mesh, and it's pretty tedious when you start working with a large amount of mesh nodes in your model. So the easiest way is to do more mesh refinement by reducing our triangle size. So this first box, when we create our mesh in the Plastics software, this first box is actually your average part wall thickness that is calculated by the system. So generally, I'll start by leaving this as the default and then going through and using the automatic and assigned size for my mesh types to see how my first mesh is going to go. The next step would be to reduce the mesh tolerance. So this is a 0.3 tolerance for the ratio. A lot of times I'll go from 0.3 to 0.25 or to 0.2 even. If I've got a lot of bad or very bad mesh elements, I'll go through and I'll change that first and then go back and remesh and see what my mesh summary is giving us. And then another thing, like I said, we can assign mesh. So the automatic and assigned size, we're able to go in and select a certain face that had the bad mesh elements on there and assign a specific mesh size just to that area. So it's actually refining the mesh. One of the areas where I always like to refine the mesh is around my gate. So I'll show you that next. So the first mesh with no refinement, if we look, like these counterboard holes are kind of squared out. Most of the radiuses are just blocked off. So it's not a really good representative mesh. You'll have a whole lot less elements this way, and it'll solve quicker, but you really want to have a better mesh. So our other option is to do automatic. So I'll come in and I'll remesh this one on automatic, and we'll see that we have a whole lot better result. So now we can see that we've got more refined in our counterbore areas. So I'm going to go through the next steps of creating a solid mesh. So this one I'll use the hybrid mesh. And as we can see, I'll rotate this around. We can see in these areas where we have the layers, the 4 layers on the outside and our layers across the middle. So we achieve that best practice of having 5 layers across our mesh. So I want to show you another best practice that I like to do with my gate or my injection locations on the model. So after we've meshed our model, we typically select a polymer, and then we go in and select our injection location. So I'll go ahead and open my injection location settings on this model. and then pick a point. I want my injection location somewhere around this area. So if I pick a point, specify a pointer diameter, and add the location. If we look at it, what it's doing, it's picking a point at an intersection of nodes, and it'll actually pick nodes in that area to represent what your gate is. So, I mean, we're able to go in and actually select more nodes if we want more area, but it's not our true representation, and it's actually bigger than the diameter that we're trying to make our gate. So I'm going to X out of that real quick, and I'll go in, and so what I like to do, I'm going to unsuppress this. I create a split line on my model like this. So all I did is create a sketch on the surface and do a split line, a specific diameter of what I want my gate to be. And this can be any shape. If you have a tab gate or trapezoid type gate, or if you have like a sub gate and it kind of looks like an ellipse, you can do that same thing as well. But this gives me a better representation of what the what our actual gate is like. So I'm going to come back in and I'll edit my solid mesh. I'll use my previous meshing parameters, so the settings that we had will come in, but I'll go in and do automatic and assign size now. I'll assign a 0.25 millimeter mesh to that area. So now when I mesh my model, we see there's a better defined area. One of the other things I wanted to point out with the injection locations now, I'm actually running this in SOLIDWORKS 2019. One of the things that they added was boundary conditions. So I can actually select this space to be my injection location. And then every time I remesh the model, I don't actually have to come in and reselect that point. And if I move that So I'm going to switch over to a shell mesh. When I do that, I'm using configurations within SOLIDWORKS. So these are actually created by using the duplicate study command in my in the system. So it actually copies a study. So you can set up multiple studies and actually run with the batch manager, run them all at the same time. But it keeps everything tied to your one model. You're not having to create different setups, and you're not losing any information if you change from one to the other. So in this one, I've done a shell mesh and actually just ran the flow so we can see our flow results. And when we run the flow, after we get through running the filling analysis, we get the results advisor pop up. So what this does, it tells me that, okay, this part can be successfully filled, this model. So this is using a shell mesh. And so after we've gone through our mesh and we've done our corrections, all of this, and like we saw in this last one, our result advisor showed us that we had a good model. So one of the things that could happen is you get a short shot. And what we should do is look at our fill results and look for a thin wall area that doesn't fill. So in this model, I've actually created a solid mesh and actually have it refined. So it's the same model, same one that we had a shell mesh on. And we got a result that actually showed that it would fill properly. So one of the things I wanted to point out is one of the most important parts is having a good solid mesh or a good mesh in your model. I typically always use a solid mesh to get my best results. So I've loaded the fill on mine on this one, and we see now that it says a short shot has been detected. So it means that our part failed to fill completely. So one of the things we'll do, we'll look at our fill results, look for the thin wall area that doesn't fill. I want to check my pressures at the end of fill and look at it for a value above the maximum pressure in our settings. So I'll go to that and show you that as well. And then a third one, this is something they added in 2018 SolidWorks, is the temperature criteria for short shots. Typically, this value defaults to the glass transition temperature. So if someone has gone in or you inadvertently changed this to a value that was, say, somewhere in between your minimum and maximum melt temperature, you may end up getting a short shot, because if any node in the system hits a temperature below that value that's in that box, it'll indicate a short shot. So I'll close the results advisor and we'll look at our pressured into fill, and we see there's this huge pressure, 715 MPa, which is extremely high. The default value for the study is set at 100. I'll flip the part around, and then we can look at the fill time on it again with the animation. And there's an area right here, there's a very thin wall that ends up not filling completely. So just an issue in the model, but it wasn't detected when we ran that shell mesh. So that's one of the reasons I wanted to show the importance of getting a good mesh. So we'll look at cooling studies. With SolidWorks Plastics Professional, you don't have the option to run cooling studies, but I feel it's really important to run a cooling study when you're running an analysis, and especially when you're looking at warpage, because non-uniform cooling is one of the reasons why you'll get part warpage. And then also, if you're trying to do process troubleshooting or optimization on the injection molding process by using the simulation software, it's good to have the cooling lines modeled in true to what they are in the tooling, and you can enter in your values and everything for the water lines. The reason it's important to have a cooling study, if you don't run the cooling study, the system's going to apply a uniform mold wall temperature throughout the process. So if we look at the temperatures on my images on the right where there's no cooling study, there's two different core areas, and we look, one of them's measuring 103 degrees Celsius, one of them's 102. So they're very similar in temperature through the whole process. The mold temperature is set at one uniform temperature. And the cooling analysis will take into account the cooling channel design and the mold heat transfer properties. So if we look at the cooling study that I've got set up, those same areas, one of them's at 91 degrees and the other one's at 55 degrees. Well, the area at 55 degrees, if we look at our top image, I have actually a conformal cooling channel that's in that area set at a different temperature than the rest of the mold. So it's actually, you're able to control temperatures in different areas. You can set different flow rates and everything within your cooling channels as well. So when we're doing cooling studies, there's several different cooling study solvers. The most robust is the Coolant flow field. It's a fully 3D CFD approach. It's also the most computationally intensive, so it takes the longest to solve. But I typically use this one because I actually get to see flow rates and the pressures in the coolant flow lines. The next one is a cool pipe, so it solves for the fluid flow using a more simplified method. Doesn't take near as long. The channels in these must be created using the runner and cooling design tool, so you're actually creating these based off of sketches, 3D sketches or 2D sketches. The coolant flow field, we can actually have 3D modeled water lines and do the analysis on those. And the third one is the coolant entrance. So you're also utilizing the sketches to create the cooling lines the same way as a cool pipe, but it doesn't solve for any fluid flowing through. So it's modeling the heat transfer by determining the convection load from the inlet temperature and the flow rate of the cooling fluid. And then lastly, we have mold wall temperature. So there's no cooling lines in this study at all, but we can actually, the magenta area on this model, I've gone in, you can actually select different areas and tell that this wall temperature of the mold is going to be this temperature. So you could actually set different temperatures on different sides of the part just for a quick analysis to see what warpage will do. So like I said, what I typically use is the coolant flow field. One of the reasons why I use this is it actually helps me achieve the turbulent flow within my water lines. So the Reynolds number is what the flow rate is of the liquid through the tubes. So the system is looking for a fluid flow rate over 4,000 Reynolds numbers. So that would indicate that it's for water is turbulent flow. So a turbulent flow through water channels is going to be your most efficient way to remove heat from an injection mold. And the cooling study within the coolant flow field looks for and solves for the turbulent flow. So it'll give you a warning during the analysis right at the beginning when you run a cool study. It'll give you a warning, as in this case is indicated here with the inlet Reynolds number of 3205. I get this warning that my inlet flow rate is too low for turbulent conditions. Reynolds number is less than 4,000. So if I get that, I'll stop the analysis there, go back into my settings and change them. And then if I run it again, we'll see if I increased my inlet flow velocity to 30 centimeters per second, then my inlet Reynolds number ends up being 4807. So it's an actual better, more turbulent flow then. So I'll go back into my model, we'll jump into the coolant flow field really quick. And this is where I would assign the different rates for different flow channels. So we've got the ability to set multiple inlets and outlets. We can set the inlets and outlets in any way we want as we go through, and we can set our flow rates and our inlet temperatures at different temperatures throughout the mold. So if we needed to run a colder area, like in this conformal cooling channel, we can run it colder than the rest of the mold. We can run one side hotter than the other. We've got the ability to do all of that within this coolant flow field setup. So when we run a cooling analysis, we can see different areas of the mold and look for hot spots in the mold. So this is a cooling average mold temperature. We can look at the mold temperature at the end of cooling. And we can actually use the measure tool as well. So we can find different areas and measure the difference in cooling in certain areas. So what these boxes do, the red box is indicated on this one area. I've got the blue box in another area. The magenta box will actually tell me the difference between them. So the 139 degrees versus 106, and a difference of around 33. So it's a good way to look for differential cooling. And we can also see down here where I've put the conformal cooling line, we have a whole lot cooler temperature in that area. A little exaggerated just to show that it's available to achieve that. So that's why one of the reasons I feel having a cooling study when we run an analysis, even if we're not running warpage, it's really important to have to get really good, accurate results. So that's it for all of my tips and tricks on making a good mesh. Also, what to do if we have a short shot, what can we look at, and the importance of cooling lines as well. Thank you. This has been Jeff Lendermon with GoEngineer. Have a great day.